2013, she's here working as assistant professor, and her research interests lie in the calculation, electronic structure calculations, both in the ground and excited state of small molecules, and she also performs quantum and classical dynamic simulation. Now she's also working on a system with biological. So it's, as I say, it's a great pleasure for tonight to have her here and to enjoy it.
Thank you. Well, to myself, so I don't need to say anything, although many of you already know me. So I've been your previous year. So yeah, Cristina, I'm going to be boring you for a couple of hours, at least, maybe a little bit less, but I'll give you some break because this is quite a tough topic. Okay? I try to make it as simple and I don't know, like friendly, because this is quite hard. But quantum dynamics is very, very big and broad topic. So you will learn a little tiny little bit, okay, today. So there are definitions for quantum dynamics. We have a definition that quantum dynamics is the classical. Okay. So basically, what it said, quantum dynamics is what deals with the motions, the momentum exchange of systems whose behavior is governed by the mechanics. Okay. So now we have a right already working. Okay, so nice. So now we have a right to quantum. Okay, so this is the key. There is another quantum mechanics, mathematics. That is the study of mathematics behind quantum mechanics. So it's again quantum mechanics. What they do specifically when we speak about study of dynamics, we still investigate how quantum mechanical observables change over time. There is another compound type of definition that I have added in a completely beautiful font, just because it's actually nothing of any meaning to me. Although now I think I don't know, but this involves the study of one parameter automorphisms of the other one. If any of you understand this, I'm very happy to you. Unfortunately, there is no definition of quantum dynamics in chemistry. I'm a chemist. I'm very, very sad that I couldn't find it. If you go to a library, it's not a book. There are no books on quantum dynamics or in the chemistry. Anyway, so if you want to guess any or even in mathematics, but if you want to actually understand anything or something, just go to the physics. You might find something that can help you. So quantum dynamics in 2 hours. With some demonstration in a couple of extra hours. I do not think that that is possible, so I will give you this little idea. If you go to Amazon, for instance, that's the one that I if you put quantum mechanics just to see, and you obviously filter it, you get more than 1,000 lists. Okay? There's a lot of people writing it because it's very complicated, so people find to see if you can understand something. If you just go to one of them, that is the fundamentals, the basics, and you get into the book, you see that you have 600 pages. I'm read that, not in 2 hours. And there is no possibility that you can learn everything that you can do with quantum dynamics. Quantum dynamics you do a series of processes. So you can study spectroscopy, you can study some issues, all sorts of things. So quantum dynamics involves everything that supposed to move things, so just see how they because when they invite me, that I just say, so when they told me what they wanted, obviously, is just that I talked a little bit about this. You know, if you already that you can study this well quantum dynamics in a time-dependent approach, that is a completely different. For a pedagogical way of studying quantum dynamics, maybe it's obviously putting the time somehow in the equations, because you always think that things move, and then you know that if they move in space and of course that makes the idea or the approach a little bit easier. I very sorry because nothing worked. My computer just to share the screen. So maybe slides are a little bit messy because I tried to do some sort of like other things, but you have to create it. So I don't know how it's gonna be. So I apologize from the very beginning. So let's move forward. I think that I assume because I don't know. Are you all physics? Minutes? Okay. At least you have heard all these things already. So I assume that you know many things, of course. And again from the board, I think that you have heard that too many times. Okay. So then I assume that you know all these already. So I assume that you know already. You already know it, otherwise come to your head. You know what is the Hamiltonian already? Something related to the wave particle duality principle, and people that you know basic unit commands of, well, you went yesterday already in some of the courses anyway, so the people who are already with PhD of course know that. But I put these dots at the bottom because I basically assume a lot of other things that you already know. Okay? So I could have list all of them, but at least you get some that I assume. Some things that you might have find that you learn just general idea of how these things are. Uh, so high school, we are going to talk about collisions. Okay, so within all the possible processes that we can study with the quantum dynamics, mechanics, I have chosen one that is related to the collision particles. Okay, so we will learn what a wave packet is. Okay, we will learn more or less how the propagation of the wave function. We will learn what a cross section is, and probably something like we might need for the demonstration. And hopefully, uh, okay. So after this brief introduction, because I have already we are going to. So we, at the beginning of this talk, or this course, I don't know how to call it, we will do a break, okay, just due to, because all the basics of the condition come from physics. Most of the beginning of the talk is based on the collision between particles given by physics, basically. So it's just like uh, they what they do is just find the type of collision that you can find, and they give us some names. Okay, so then you always see that that they or they draw are just like beautiful circles like particles. Okay, like a ball. Because obviously all the basics comes from spheres type of conditions. Okay. So we will be, I hope that, so one of the main ideas of this course your brain open just to make the connection between physics and chemistry, principles, and what is, well, here basically what it might not be some chemical reactions. Okay, so then um, let's see what happens if we have two things colliding. Let's call them things or particles. We can have what is called perfectly elastic. Basically, they collide and they, somehow create something completely new. Okay, so basically, is the idea of chemical reaction. Okay, the idea of a chemical reaction is that you have A plus B, and then you create something else. But then we can have something completely different that is elastic, what we have in a billiard table. Okay, that you have something, collide with each other, and then they just go away with different trajectories. But nothing has actually happened to the flat spheres. Okay, that is obviously something that can be studied. It can be of very high use in chemistry because you create things, well, you make a fragment, they might not collide, but when you just to transfer the energy, translation energy, vibration energy, or rotational energy, also because you create in a different, you know.
Yes, the sound, please.
Okay, so this is one of the things that we might be trying later in the demonstration, if everything works, of course. And then we have what is called inelastic. Well, that is in some books they call it absorption. Okay, and it's just like they collide, and some part of one of the fragments, well, or basically both fragments. So you get different, but you don't get different. Well, these two, sorry, these sorry. So these two are always saving most of the energy. They call it plastic and they call it plastic, but closure. In here, it's perfectly unplastic. So let's begin a little bit of chemistry first. I'm a chemist, as I said, we'll do it. So we all know that we define chemical reaction by a chemical equation, and then in a very general way, we can make A plus B to obtain D, C, and D. I don't know for the physicists if you have ever seen this. Okay. This is how chemistry we calculate this rate of a reaction. Okay. So what we do is that we can obtain from the rate constant or the speed basically. The rate of our reaction, basically seeing how the concentration of the reactants changes disappear or the appearance of usually all the time. This is some constant multiplied by the concentration to the uh, uh, the order of the reaction. Okay, so then we can have a first or the second order 1.5 or 0.5 order of the reaction, and it all depends on the speed of this reaction. Okay, as you see, the rate constant is something that depends on the temperature, of course, and this is something that for the chemist, I don't know, the physicist, it helps the reaction. So basically, when you increase the temperature, molecules are very faster, and you kind of help the collision, and help that you get extra energy to actually reach. Okay, so this is the main idea in chemistry of the rate constant or what is physics. No, that's rate. Then we have a dependency of the rate constant with the absolute temperature, that is what I said, and this is governed by the Arrhenius the radius gives us the dependence to per node, okay? And then the R constant here, where the E sub A is the temperature, the and R is the gas constant. But if we talk per molecule, this is something that we will want, okay? Then instead of having the R, the gas constant, what we have is both constant. Okay, so somehow we can obtain this dependency with it, and then that will be something we will use at the very at some point. We will obtain the rate constant. So the thing is that you might think that obviously we're talking about actually a chemical reaction is kind of a microscopic quantity. Okay, so we need because the, the topic is quantum dynamics, so then we need to go from something that is microscopic to something that is uh, okay. So then, how are we going to change something that is microscopic from atomic scale first? So this is where quantum dynamics or quantum mechanics starts. So the phrase itself is interpreted in quantum dynamics in terms of this quantity that you will see many times in this talk. That is called the cross section. Okay, it depends obviously on the section for the reaction between two fragments A and B with a particular kinetic energy. Okay, so the relative energy, the relative velocity. So basically, the cross section for a reaction is a proportionality factor which measures the likelihood of the reaction for A and B in the specific way. Everybody, or especially, not probably everybody. You have heard these things. Doesn't matter how fast you collide, but you need to have certain conditions. Part of the idea, the likelihood that they have. So everything is going to be related to that. Okay? So this will give us all the information basically. Give us likelihood is very similar to probability. So this is one of the most important quantities that we use. So then, let's start from the very, very beginning. Let's think that we have a set of fields. Let's start with circles, just circles, one dimension. Okay, nothing can do a lot of these things. Okay, so then we have a particle A with size that obviously is related to radius, very very rough. And then we have another one that is with a different radius. So we define the two velocities, obviously when these are radius. Okay? But these we can define the relative velocity between two particles in this pictorial picture here, and then we have the relative velocity that goes. Okay, and then we can plot this passing through the middle of the area of both of the particles, let's call them. Okay, and then we can define, because those are rigid, we can define this, there is the impact parameter. I suppose. Hopefully there is a anyway. Because I thought that was anyway. So we can find this direction or the line that we can actually follow, passing through the velocity vector that is the relative velocity vector, and another one that is parallel passing through the middle of the. Okay, it's the impact parameter. So we have several possibilities. Well, we have different possibilities. So that we are in the quantum realm, and then we have what is called a potential. So these potential energy that you feel, we can, when the particles get very close to each other, so close that they cannot actually pass that because they are immediate, we kind of mimic this situation with a potential that is infinite. So you cannot go from one particle inside the other. Okay? And then we consider for the rest a free, so no potential whatsoever. Okay? Actually, what that means is that two particles can actually touch each other. That is a very important thing. If you think in chemistry, atoms cannot close as one atom to the other atom because we have a potential. Okay? So that will be something that is very important to remember when we start talking about chemistry. Okay? But in this case, because we want to start the basics, we have to think in the most simple way. Hard spheres, no potential, no any other thing is changing my system. Okay? So then, as I said, this is the parameter, and then when these two things are close to each other, because they go with particular speed, velocity, so energy, obviously, with the momentum, and then something will happen. But then they will go different directions. This direction, with respect to the relative velocity vector, is what we call a scattering angle. That is this theta here. Okay, and then if we draw a line between the two middle of the both particles, this line that is here, this dark line that is here, we know that the half of the pi minus is this other angle that is the one that is here. This is actually yours. Okay, so if you could have this, you may see it. Okay, so it's this angle. So the idea of all these plots is just to understand that the impact parameter, the scattering angle is going to be related to, of course. Okay? And this is as well something very important because that will give us, so think that now we are thinking about hot sphere, okay? But we will be talking about molecules, even a nitrogen molecule. It will be very different to this type of impact parameter because we will have some very large figure. So you can write, imagine that this is the side or in the middle of the molecule. So everything will be very different. Okay? And that will make a big difference to occur. So we can obviously define kinetic energy with respect to relative energy. Velocity yours. Okay. So this is the idea of the process that we need to set. So in classical mechanics, so yes.
The previous slide. Yeah.
Wait.
We are not considering the mass element, right? If we are assuming that the mass B is bigger than A, so it's even. Okay.
Yeah, well, obviously it's something that it will be, or the thing is that, well, I didn't say that this is a very good question, that this mu, okay, it might be some mass, some height, okay, so it might be like the reduced mass, or, okay, obviously the mass is going to be there because it's directly related to.
So you
Oh, sorry. I'm sorry.
I'm not just 2 minutes. So the mass of like if we take the fact that mass of A is bigger than mass of B, then I think the angle will be
Completely different, of course. Well, not only the mass, the size as well.
size.
I think that this is one of the possibilities, okay? But the both things can collide with a much larger impact parameter, well, not much, but a little bit larger, and then this A particle will hit the B particle very high. Everything can change. So it obviously makes a big difference to have a bigger. So I will go back and forth from the classical mechanics because obviously it's the easiest way to understand things. Well, easier, at least just make the connections between things. So as I said before, we can define the sign of this angle psi and the sign of the half of pi minus b. Okay? And this is just by the definition of the sign, basically b over r plus b. And in general, we can define some dependency between the scattering angle and the impact parameter with an equation of it. So that obviously the impact parameter is related to the scattering angle. Obviously, because the impact parameter is so high that molecules even see each other. There might be an equation that actually govern this dependency. Okay. So let's go. So this was very brief, but life is not in 1D. Okay. So everything starts getting a little bit. So now let's think that reality is. So then what we have now is obviously here. Yeah. So then we can have something that is the B, the impact, and then we have to study the possible variations of these B along the directions, basically. Well, not all, basically, because they're talking about spheres anyway, so at least they have certain differences, so they change, and they see how the cross section change or how the antenna change. And we have B plus a delta B. Okay, find the differential section. Okay, that's 2 pi B equation. Then that we can now collide from this the inner cycle B plus this times B, then we can obtain an angle theta, the one that we had before, but then we have as well the other angle that comes out of the screen. Then what we can define is a solid angle. Theta is this omega. Omega is basically both angles together. So the solid angle, the definition of the solid angle is the r squared is this one like that, 2 pi minus theta. And then we can obtain this omega, this basically. So I think different, but now try it and follow my pointer because otherwise it's too much information. Both in classical and quantum mechanics, scattering phenomena characterized by this scattering cross. Okay, there is some likelihood of the process to occur. So if we consider, so now think in the new system, think about collisions like a flux of particles. Okay, we call it flux of particles here. Okay, well, we have not it's a well, we call it flux, but I don't wanna use the flux word because it's very easy for something different. So we have a number of particles, okay, just colliding, just going in the direction of something and colliding with something, and then we have this J, that is the number of particles per unit time. Then these flux actually can be defined as the number of particles that cross some surface that you put. Okay, so in mathematics actually, you can calculate the flux of something, just call it if you place a kind of surface and then you see basically what goes. There is a way, a mathematical way. Okay? I didn't want to use the flux word before. Okay? You can measure at any time how many particles are going through. Okay, this is one of the analyses of most of the processes that we study. Time. So we can, the collisions that are characterized by differential cross-section, that is the ratio of this number of particles into any direction. So think that you collide and then you scatter. And these are, okay, is what we've been talking about. Then what we are going to do is like the number of particles that are actually collided. Some of them are scattered, okay? And these number of scattered molecules, where the direction, actually, the photons in the three, is what is what we call differential cross-section. Okay, so N here is the number of scattered particles. Okay, obviously, if you want to know how many scatter from the initial number of particles that you actually set collision, obviously, ratio between them. There is this is like any other property that you might actually want to. So from the yes.
How will we can consider that a molecule becomes treated as a particle?
Again.
How can we treat it as a molecule as a particle? Because particle definition is different. And
Oh yeah, no, of course. We still in the most basic part of the course. We haven't talked about molecules so far. No molecules yet.
Okay.
No molecules yet. Okay, I need you to understand how the process goes. It's a completely different. Everything gets you don't have spheres, of course. Okay, so but we will get a little bit. Okay, for the total, so we can take the differential. Obviously, we can take integrating the total, of course, and then solid angles just by using integral. Then the cross section depends on the energy, obviously, of incoming particles, of course. It has an and can be separated into the different processes. So obviously, in a perfect world in which we could calculate all processes at the same time, the full process will do all the possible processes. That is utopia. Okay, there is nothing that you can do. You can do all the processes at the same time. Classical. Okay, so you can divide the different processes somehow, but in quantum dynamics, you basically separate it briefly how you do it. You can. It's a very complicated thing. Okay, so we sometimes separate to study kinds of processes because there are many things related to symmetry and numerical methods, the things that govern or calculate better these. So before, so before we move to the quantum scattering, we're going to go through a little bit to the. I don't know if you've seen something related to quantum scattering with Brazil. No, not at all. So let's move a little bit to just briefly give a few ideas that I think that you in mind. In classical mechanics, if we have a central potential, V, the angle of scatter is determined by the magnitude. So the number of particles scattered per unit time between is equal to the number of particles per period time between B and B, and this is what we have the delta B, or what I said before. Okay, so this variation of the parameter will affect, of course, the angle of scattering. Okay, so then if we have an incident flux, okay, the number of particles scattered into the solid angle per unit time can be obtained by the two equations that I have already included in rearranged. We say the differential cross section as something that depends on the variation of the scatter angle and the variation of these impact parameter is dependent of the scatter. So the classical theory basically, if we again these plots, so we have this impact parameter B, we collide, we create sections of the theta, two angles on the for the elastic scattering, as we know that the beta define this. Okay, and then we can obtain the derivative of this impact parameter by the angle, and then we obtain the derivative of this value. That is the sine of the angle, and then we obtain this cross section. This differential cross section. It would be equal, what we are saying is p squared. So the theory actually has to be that the total scattering cross section is the projector area of the sphere. So basically, if you have two spheres, the likelihood that the collision actually happens, it can go further than the size of the sphere, because then they don't touch each other. Okay? Easy? So far this is easy to understand. There is a little bit of geometry, but if you go through slides later, you will quickly understand this. So then, maybe I can just give this, and then we have a break, and then you talk a little bit, and just go to the loop. So let's go a little bit to the for now, if we want to consider the real world, the real, okay, like collisions of an electron and atom, or alpha particles on the nucleus, molecule, whatever. In principle, the particles are represented by wave packets, and then we will go there. It will be that is governed by these, probably known by all of you independent experiments there. So, if we can study and we can solve with this wave packet, we can find the probability amplitudes of the outgoing waves after the. So then that will give us the scattering angle, the cross section, and everything. So everything now related to how do we actually define our particles. Now they are not spheres. They are not IRs. They're completely different. Okay? So I don't know if you have noticed already that the R is here. So now I have assumed, of course, that you have known, studied already human information, both moves or the move of the elements are included in this term, and now we are not talking about it anymore. This part of the equation that is always out of your lessons. Okay? Everybody does the information, and then they forget about the nuclear. Nothing is ever known nuclear for some. Okay, probably it's because it's much more complicated. Okay, this is incredibly important. Okay. Now I assume that you understand that this V has already everything related to electrons. Okay, and then we are going to move them. Okay, so now I'll give you some time to digest that. It's 12:33. Maybe we can be here at, I don't know. Okay, just hold. Oh, okay, yeah. Yeah, exactly.
Probably it could be the conditions and no mathematics
¿Vas fuera o qué? ¿Tú me vas a hacer? ¿Ya ando ya? ¿Estás oyendo? No me oyes. ¿Me oyes? Un poco, vale. Hola, Juanjo. Le podemos decir todos algo a Juanjo que nos está escuchando. Porque no tenemos un Juanjo. It's actually hello, Juanjo. ¿Ahora sí? Everybody back here, or are we making? Oops, you see? Oh, I hope that. What if? Juanjo. Okay, things are gonna be tough from now on because there's plenty of equations. I'm sorry. Anyway, yeah. Okay, so let's continue. So now, what we know is that if we want to consider the quantum world, what we're going to do is just to solve the independent explanatory group, in which what we are going to study is instead of a set of particles, what we're going to do is just try and define these particles as wave packets, okay? And then we will obtain the various amplitudes of the going waves, and then we will take what is related to the or to the parameter or to the level of things. Okay, you will have to believe say I right there. I'm sorry. I don't know if you've ever seen these type of expressions, but we will try and check out so that you can see what I mean. So if we have a wave packet, usually this wave packet has a well-defined energy. So what means that it has a momentum, okay? And then we can consider the wave function between or the wave function that we would use to create a wave packet. What is called wave wave. Okay? This wave, what it has is this psi dependent on phi and psi. And this is called another psi that is dependent on r, and another exponential to the one I h bar. Okay, so we have this separation of variables that is okay. We can define a function multiplication of functions of the different variables, right? And then what we have is one function that will have the position of the wave packet, and another function that we will give us how it will evolve in time. Okay? And then if we look for the solutions of the time independence of the equation, this is something that you have already seen. You take out a time, and then solve the time independence equation, which psi is. This is wave. Okay, so where h is already defined as the kinetic energy. And it gives us the other body that is the wave. Okay, so if we have some boundary conditions, then the incoming component of the wave function that is displayed wave, okay, we can obtain the flux using this flux operator that is what I said before. So this is the definition of from our wave packet, we can obtain the flux over a surface, a perpendicular surface, just doing this operation. Okay, and this is this ends up having this. What is a plane wave? I think that you have already. It's not there. Anyway, this is not, but there is something underneath this. So in an electromagnetic wave, if it has a defined frequency or wavelength, it's what we call a monochromatic or plane wave, and then they use monochromatic one light, and then you go to red or orange, yellow. There is no monochromatic light at all. Okay, people try no monochromatic. If there is those two, it's very complicated. We can define this type of plane wave in a very easy way, just like an amplitude is zero multiplied by so it's something that oscillating in space and time, and this is obviously the definition of electromagnetic wave, which we have two fields perpendicular to each other. And the magnetic population will be okay. This is the type of wave that we okay. So basically, is the type of wave that we have in our head when we think wave. So then, this is we can express this sinusoidal type of plane wave in terms of a okay. So if we have this equation, we are going to relate somehow to this exponential. Okay, so then we know that we can write this one exponential as the sum of the cosine plus the time. Okay, and if we find the wave function as using this definition, we can see that this person is the real part is the real part of the wave function, and then it's equals to this thing, this way of defining wave. So then we know that if we, in this case, include this a times E0, a times 0 in here, then we know our wave function can be right this way, basically obtaining this pre-factor that it will be related to the time amplitude, to of the phase, that is something. Then it's to the complex number K, R, and omega T, where I didn't say it before, of course, zero is the amplitude, of course, of the wave. R is the direction BR. Omega is frequency, time is T. And then psi is the phase, the wave. Okay. And this is why I go read phase here, just including constant. It's the factor 5. Okay. Then we only end up with the one function just as an exponential to the R and omega. So the position and the frequency. Okay. So I think you might understand already that this defines energy and momentum. Okay. So then, because in the previous slide, what we have is actually wave, because we have arrived to this expression from the plane wave, so it's one plane wave. And as I said here, it's actually infinite, okay? Because this will oscillate in time, okay? We need to have something that actually different to particle, and a particle is not infinite. Okay? So then we need to create a wave packet. And it has to be something that is that has a certain size, obviously, and it might be related, of course, to the size of your fragment. Let's call it the fragment, okay? And then what we do is we have several plane waves, many as we need, okay? And then if we make a combination of them, we will obtain what is called the wave packet. How do we get that? If we make a linear combination of these plane waves, if they are, none of them are in, anyway, we will see that in some of the next slides. Anyway, so something that you might end up with a part of the wave packet. Look, if you have these plane waves, you make a linear combination. There might be some of the plane waves that actually have maximum in the same position. Okay? Then those will sum up and will create something like that. If they move away from this point, for instance, in here, where both are very near, the maximum are very near, move away because obviously these amplitudes will be different. These will create these different amplitude defined. So the end up is with a wave packet that actually has in a certain amplitude. Okay, that is what is related to the multiverse uncertainty value that we talked before. So we know that we can make this superposition. We can make this combination of different plane waves, and this is what we call summing up a total number of plane waves to create a wave packet. Okay, and then this what is the lower part of this. It's just the real part that is related to the information. So in the case of this is again some of the obviously accept that you knew is that we can define matter in the quantum world as waves, of course. So in the case of matter waves, the wave properties K and omega are linked to the momentum and the those equations, you know. So the energy is equal to h bar omega, and the momentum is h divided by the weight. The previous slide. And then h bar times the weight with weight. In quantum mechanics, when a particle has a definite momentum, its wave function is called plane wave. That's So this is the idea of talking about plane wave and talking about wave function, and then obviously coming up into the wave packet. Okay, so we will make a full set of waves that define different momentum. Okay. All of them are wave functions, and they're at the end of the explanation. So we go to the free particle case in which we consider that the is zero. Okay? No potential. Ideal thing, okay? And then the only thing that we do is just to apply Hamiltonian. That is just the magnetic energy. Okay? Then plane obviously the other stage of the is something. If we use these expressions here, then we can express the wave function this way. Okay? Which now we have the momentum and the energy. So then, depending of the way in which we apply the Hamiltonian, we can actually get how this wave function changes in space and in our. It is obviously the multiplication of two exponential functions, one related to the momentum and one that is related to the energy. Okay? And make this clear. So now we have this definition of the wave function, or I always speak of the wave function, but obviously the wave packet would be a linear combination of several of them. But we can treat them all individually because each of them has a momentum. So we need to know that this wave function satisfies these dependent and determined independent influence. So we need to know that wave function is an empty state of E and T. Okay, so I mentioned that okay, the equation is like this. It satisfies the independent equation. So we can see that there is no potential. The application of the operation would give us the identified the energy identified, the energy that you are using in quantum chemistry anyway. And of course, it satisfies, otherwise we cannot continue with the quantum. It satisfies the time dependent running equation by the. So now let's summarize a little bit some of the concepts that we have studied about the. So plane wave it works. So although having a definite momentum are completely delocalized, okay? So then you can obtain a localized wave function, but supposing the wave function. Okay, which is how do we actually make a localized equation, some function that we can actually an infinite way is really constant. We need to have something that is in a certain place in space, that it moves and not something. So then we know is just creating the wave function. What we say is that any localized wave function expresses a superposition of infinite waves of different momentum, and there's the momentum of the particle is no longer an the coefficient in superposition represents the amplitude. This is something that I don't know if everybody actually know. We have a thing that we have. I cannot see the yes, in here. I don't have this question here. I have it in the slide that you see properly. I don't know if you all understand this. If you have a function that is a three-factor value like a, the one that I put before, and then you have an exponential that is to the power of a complex number multiplied by whatever, okay? I know that the probability of a wave function can be doing the, yes? Okay. So if you make this exponential to the minus I, blah, blah, blah. If you use the thing, you get 0. Then dA is where dA, it will be actually negative. This is the D here. Okay? Because that will be in all the cases, every time that we will speak, we probably always talk about the factor part. That is not the exponential part. So this coefficient, that is such a superposition, okay? And then it will be so one of the things is that in quantum mechanics, obviously the wave packet is the most particle-like the wave function. So basically, it's what defines a quantum. A particle, the meaning particle, I mean fragment. Okay, because we are talking about a particle like being a sphere, as the ones that we have seen before. Obviously, it's easier to obviously study this, but you need to think that every fragment can be like a molecule. So we can create wave packets defined. The only thing that we have to do is just to be able to define a wave packet of them that actually defines a diatomic molecule. What will define a diatomic molecule? Maybe vibrational states in rotation. And then you make a combination of these type of functions, and then create one of your fragments as a wave function of a particular diatomic. Everything gets more and more complicated if you think. Because in physics, if you talk about hard spheres, everything is easy. But if you start including different properties, everything has to be defined by a function. If you want to define the vibrational state, you have to create for the vibrational state. To define the rotational state, you have to include. And then you have to go back to the wave packet. Then it's only one fragment. You have another fragment on the other side because you want to collect. Then you have to create another wave packet there. Then you have to create something that actually study the collision between them. That is something that's actually the only thing that we have been talking today. We haven't talking at all about these fragments. So everything more and more and more and more. So it looks like when you go down into quantum, everything will be easier, but no, it's completely the opposite. You go to the quantum world, everything is competitive. You go to bio and very everything is easy because it can be treated. So you use the this is easy to understand. Okay, so this is more complicated. So this is why in most of the books, it's just like hard spheres, those are the questions whatever. But these you have to actually describe the fragments. Okay? Because seeing a plane wave moving is trivial. You can just define a function that moves, and then you propagate it, change everything. And then you use the scattering definition, you use the cross section, the scattering angle, apply these a couple of integral. What happens when you have something that can actually collide? That's changing, or this starts changing. Everything is more and more complicated. Okay, so then we can go through not in 2 hours, not in a year. Okay, we're doing that for many years already, and probably I don't know yet because it is everything. So it's not very complicated. There's a lot of symmetry that we will have to introduce. a lot of quantum, angular momenta and things like this are incredibly complex. So, one of the main things we need to know is what a Fourier transform is. Okay, because Fourier transform is in quantum mechanics something that we use for observational basically. Okay, but one of the properties of Fourier transform is that it allows to remember that we have a wave function, and then now we have used so then now we have our wave function. Here of this one. Then you remember we have two terms here, and one is related to the position. So if we choose the first instance, so when t is 0, so we always play like this, okay? Just making one of the sides of this wave packet 0 to make our life easier. What we get is obviously the definition of the wave function, only dependent of the position. Okay? And then we get the wave packet. Fourier transform. I will give you some bibliography at the end of the you might know them already. Just the Fourier transform is something that you get in no confusions. There are libraries that you say, Fourier transform this. Okay? So you go from the position of your wave function to the k. This wave function will be related to the momentum. Okay, so just doing this transformation, you have both the you can go from position to moment. Just doing this. Okay, there's a nice demonstration in which you change the energy and the momentum. I mean, it's very nice and web page. It's in there, so you can check later. So then, before you transform gives us that, it gives us something as well that I don't know if I don't have the time to tell you that is related to the derivative of some of the propagation in space. So the Fourier transform is as well used to calculate the derivative of the wave function over the position. So let's go back into this. So imagine that we have three waves. This is the one I want for. Okay, we have the three different waves. Okay, where the center of we have the center of our wave. Okay, the three waves are all in phase. So you see that the maximum of the three waves are at the same place. Then obviously the combination of those will give us the maximum of the wave functions. But obviously because they have different here, obviously they interfere destructively. This is why it will create beautiful, not infinite way. So it's very well localized. Okay, we have the difference or the relation, sorry, between position, in this case, is related to the momentum. And then in here, what is plus is obviously possible possibility, okay, in which we have the uncertainty of the difference in position, and we make it bigger than 1 over the uncertainty of k over momentum, or when it's much smaller than 1 over this uncertainty. So if we have this uncertainty of position much larger than 1 over k, we see that we have oscillations. But if we do it the other way around, we barely. So this is the Heisenberg uncertainty. Okay? This is the way in which we get the uncertainty principle of k. You say, well, maybe, I don't know if it's this, yeah. So I'd rather prefer to have it between the velocity and the momentum itself, not like this. Okay? So then, because we have a plane wave that corresponds to a constant quantity of particles along the axis, only one angular frequency, one wave vector, because we have seen the relations of E and RK, we end up having this other equation in which instead of having the A, we have the okay, so it's momentum, then we can obviously transform this, and then we can go directly from position to the okay. So then again, because of integration, we can interpret C K. You find it in momentum, and we have this definition, we will say this value of each side on the momentum might calculate. Okay? And then instead of having now the principle with XMP, now we get the principle XMP, so the position and then we can so what do we know so far? That's it. From particle physics, we know that the concentration is a proportional constant. We know which measures the size of the molecules. I don't know if you have made that relation. I don't know if I have emphasized that enough. If you remember when we were talking about the spheres, one of the things that we actually use as a condition is that we do not get closer to the radius of both. Okay, so then the and everything related to the cross section, related to the shape and the size, the way in which they collide and the scattering angle actually was defined, and obviously some angles related to the sphere. Okay. So then somehow this cross section it might give us some idea about the shape what we have. Okay, because at the end we end up with this pi r squared divided by, you remember, it was actually the size of the sphere. So we need to make this connection that this section it will give us the effective size of the molecule. Okay, so then this is why is the likelihood that the collision between the molecules will lead to this. So the likelihood is trying as another way to say probability. Okay, that's a nice word actually. So how do we get probability out of the way? Obviously, because we know that we have the probability amplitude of the particle presence, the probability density is the function. If we do the square of this function, we will get the probability. Then, at the second time, we will obtain the probability in position. So it's what I said before. When I want to show something, I put t equals 0. Okay, then I could say the probability in position. So if I choose a certain position, then I will get the amplitude or the probability in. This is a good thing about this with definition using the wave function. So then this is why it's written in. And then because wave functions they correlate with, and because of these separational variables that we already mentioned, we identify wave function or wave function that is the side related to the position, another function that is high here, no? Here is going expected time. So these are just a wave equation now. So now we are with brackets, we can now our sphere. We have this this with potential equals infinite or 0. Now we have a potential. So this is why I included this. Notice that the four spheres the potential of zero, so it's like a possibility, of course. So the particles will approach to each other till the point in which they actually will collide each other. But you always you compare things by the potential. Okay, you have a force and the potential, and then you will have a function here. And this function, well, this property here, and this part is coming to part of the process. So your molecules will come as close as they can. Because this is the more concentration. Okay. So when they get very, 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 very close to each other, you get a barrier that goes then depending on the energy that you give into propagation, obviously, it will reach higher energies of these barriers. So they will go very, very close, but never closer than one in. So it is included in the equation. So plane wave, I think something many. I'm sorry, but not to keep that. So the plane wave is a solution of the Schrodinger equation. Okay. So the type of Schrodinger equation is like this. Okay. I don't know if you have actually thought, because before I studied this type of thing, I didn't know how you actually solve the. How do I know this? Now what? How do I put that? What do I do? I have an equality and solve the differential equation. I do that. Okay? You define your wave function, blah blah, and then you have to apply the Hamiltonian. Then you have as well a here in which you have to make the equation of time. We give you the solution of the wave function. Okay? So this is why it's the equation. Then you have the part of the function that is just taking the position that you know that is the solution of the time independent. If we define the Laplace derivative here, the Laplace in critical polar coordinates, that it will be something that it will help. We will define the collision, and it will go into the three directions. Working with precision is a little bit more complicated to understand. So basically, use two angles that we define, the scattering angle and the other angle that is on the screen. Then we can define or write the Laplacian instead of Cartesian or the types of coordinates like the square coordinate. And the Laplacian is like this square of it has this coordinate. So to solve the left side of the equation, okay, we need to find a function, right, that at time equals 0, so forget about time now, because we are only applying time here. There is a second derivative in position and multiply by the sum that is potential by the wave. We need to find wave function that actually is an eigenfunction of this operator. And these are these functions. Okay? So we again use distribution particles, and then we have a function that is dependent on the distance between the two fragments actually. Okay? Because this is the actual coordinate. So it's the relative position of those fragments. Okay? And another function that is defining the angles, the scattering angle and the just in quantum chemistry, you have accepted that the eigenfunctions that we use to actually solve Schrodinger equation are Gaussian functions, for instance, that are sets. process, although there are processes in which they use Gaussian in this case. So these J are spherical Bessel functions for the case of the application of the Hamiltonian, and the other the Y are the spherical equations. I have already heard that. So if you choose your functions, so those functions, you make sure that these will fulfill what you need. Okay. So in the absence of a potential, so when we have the both brackets, okay, L plus L multiplied by L plus S for H squared is identified with the angular momentum. And then you can have the projections of this angular on the you can define the angular momentum. If I start with angular momentum, we will need several things to understand this. So then, think that you can have an angular momentum well defined when both fragments. Okay? Because you know what is the eigenvalue for the application of the momentum, then I don't know if you know. We know that these values are these L plus L. Okay? It can be included in the equation. So we have the first term that is the kinetic energy to the derivative related to multiplied by the function. And then we know that this is now, there is another thing that you have to relate. Now, in quantum mechanics, the impact parameter is based on the projection of L. Do you understand this more or less? Remember that it was this the distance between the two centers. Okay, when they the relative velocity and the other value that it was parallel, and then you define this difference, this distance between those. So now this is related to angular momentum. That's something that it would be like different from parameters. Okay, so this L replaces the impact of classical. Okay, so this is now substituted. And now we have something else. We have the other side of the equation. Then we have to solve it. Okay? Because well, I'm not saying because I find it sometimes complicated, but I find that I have to repeat it. In here, you only have derivation in position. And in here you only have for different in time. Okay? So they have to be solved somehow separately. Okay? So then now we know that we have this, we have to solve the related to time. So then if we have now solved the part of the Hamiltonian that is related to position, we apply this equation, apply to this high time equals to this, finish this equation, and then we end up having this. We don't know how to do this integral, we know that is a logarithm, then that the inverse of the logarithm will give us this in which you have the Hamiltonian. Remember that the Hamiltonian only related to position. So then this is why it can be here, having no problem. But it has to be the kinetic operator and the potential operator. So then this is what we call the evolution operator. So then what we have to do, we have a function, we have a well-defined position, and we also have it defined at times 0. And with this evolution operator, we will see how this function will evolve in time. Just apply this operator. Easy. We have a function, we multiply with that, we know that this is a derivative, that we apply, and then we see at every time step how it changes. And we will put this value of the function related to this one into this again. We will solve the left side of the equation, right side of the equation, and both coming back. And then you will see how your molecules get close to each other. And see what happens. This is why time dependent is the easiest way actually than quantum mechanics. This way. Actually, based everything is a little bit easier. So this evolution is calculated using a time propagator. There are many different. Okay. So we have one of the most common ones that is a Schoenchef operator, we have a speed operator, or we have some other alternative types of. It doesn't really matter. There are numerical methods. Okay. Numerical analysis that you might end up knowing or you already know. There are millions of different types of ways. There are many different numerical methods that you can use for also applications to this chemistry. So, summarizing what we know already. Now we are in the chemistry world, and we know that we have microscopic world, which we have the potential energy forces, okay, to give us potential energy surface, quantum chemistry, okay. For approximation, you take out the big iron, relate to nuclei, and then you end up having beautiful things that you already have seen many times. So, using the structured simulation for a particular impact energy, you will obtain the reaction. And as I said, because before we were related to the impact parameter, now it will be related to the angular dimension. Okay? So the probability, as I said before, it will come out of probability of the density. Okay? So if you integrate impact parameters, in this case, the sum of cells, you will obtain the reaction cross-section. This is when we connect. After we get the reaction cross-section, if we multiply it, because this is something important. Now that you have, that we have been talking most of the time about like one collision, okay? And then we have related a relative collision between the two fragments, okay? But in the real world, of course, what we want to have a over magnitude, that is spectroscopic magnitude, will be a very coefficient, very constant, that is obviously related to having several molecules, several fragments. And then you will have to define somehow the velocity or the speed of the fragments, or more all the fragments will have the same velocity. No, your beam, you can have a beam, put all at the same speed. You will end up with having something that it might usually collide before, lose some energy. So then you will have to multiply this cross-section by a relative velocity, and then you will obtain the velocity-dependent rate constant. Okay, so you will have the average of the speeds. Then you will find a rate constant that depends on the speed, basically. And then, because as again, that is just considering non-temperature whatsoever. Two things are present, that is non-temperature. So then you will have the temperature somehow. do is just you do a thermal using the Boltzmann distribution of B, and then you will end up having this. So we have gone from the microscopic curve into the microscopic one, just using this wave. Okay? It's basically solving the equation, typing the equation, and just making it after you have solved this for a certain time, you have a function that is being evolved in time. Okay? Function that is combination of these fragments and then go closer to each other because the evolution of time operator, you will the function and then after that make this square, just give the probability, integrate that, get the cross section, multiply the interval, the velocity, use Maxwell Boltzmann, and then so it's all numerical methods. Okay, these and these, apply these, and at the end it's all time. Okay. So this is how we end up getting the rate course. Okay, obviously, you have understood the idea of the packet. The wave packet itself is a combination of waves that will define either of your fragments. Okay, so we said that we can include a set of momentum, A, sorry, or K, and then we will have separate values for the momentum. Okay, but you set some value, you will do a angular momentum, blah, blah, blah. So everything, because this is mathematics at the end of the day, it's everything. You will end up with a set of values defined by your quantum number and your all the things that you include. Sorry, if it is a molecule, fractional values of your initial fragment, all these. So it's not that you can make a calculation that you will include all possible elements, of course, for all possible values. So you will have to calculate these microscopic things. I hope that you have got the idea that it comes to a law of propagation. Okay? Because the wave packet will define initially your fragment in a set situation in which this fragment has, I don't know, vibrational state equals to 0 or 1 or 2. And a momentum that is equal to whatever. And then you propagate. But if you want to be equals 1, create a wave packet again and propagate another one. If you want another one, so you understand what I mean? Then just getting into these a lot. Okay. Because if you want to actually the Maxwell-Boltzmann distribution of different B, you need to have different calculations. So it's not that you propagate once and is out. Give me the gross. Okay. This is quite, and those calculations you design for your system, they are quite complicated. Very time consuming. Let's see some troubles that we can find. By trouble, I call them trouble, but it's like something we have been thinking in no simple way, but we need to go to chemistry now. Into the fragment. So then we have considered rigid individual particles. So, but chemical reactions, of course, happen between the molecules, atoms and molecules. So if that is a spoiled as well. I was supposed where I asked you, but it doesn't work anyway. Can we consider the molecules as a part? Of course not. The structure of the individual particles will make big difference on the cross sections, and as I said before, it is all the way that the structure is affected by the impact parameter yes, angular momentum. Obviously, how is your separate fragment? It will make a huge difference because it's not a huge biochemical molecule. We collect with a little electron, for instance, or it's two fragments, and one is an atom and another one is a molecule that is collide in all different. Obviously, these restrictions will be affected by the size of the shape. So the answer is no. Okay. So on this two at the bottom, we have one possibility that is the collision with ozone. Okay. We have different types of collisions. In this case, okay, we have so they can have the of this molecule in which oxygen is on the side of the ozone, and then they know that when they collide, they create okay. So we get so we have it on the other way around. We get the okay. So they call the effective. That if they know that if they collide on this way, any break of any bond. But instead, if we have this type of protein in which they kind of parallel, okay, they see is this coming from the collision can transfer into some of the vibrational states of the triatomic molecule, the ozone, and then you can break these and then create two different groups. So this is what we meant. Well, this is what they meant all the time. Like it doesn't matter how this speed is, it's just like the collision has to be well. So this is it. If you could, I think, if you have a molecule, it always it will be covered more of it. You will predict slightly how the collision could be when you see the potential. Okay, so this is why it's important to be honest. Because you think that you have a diatomic molecule, for instance, and then if you want to get these because you create collision, because you think that you can end up if you have a lot of energy, right? This will start vibrating, and then oh, so that this might be break at some point. Okay, this might break at some point because you have given so much energy that because it vibrates so much, it might end up reaching the top of the well. Right? Doesn't mean that these is to find you to actually join them back. So if you want to keep this activity, you will have to change the orientation of that molecule. And then you will see if you get this possibility. But this is the thinking like in the classical way. Okay? I think that you have a potential. And maybe because chemistry, this approach, it has a huge value. Okay? So this is why they were very clever when they made this cartoon here. Okay? Because they didn't put that right like in a perpendicular way, like the other molecule like this. So probably because the barrier to reaction is very high, and we will see that in the demonstration, hopefully, this after. Okay? Then this is one of the important things about it. So now things get a little bit more complicated. First, we need to see how the is, and then see if we can actually see how reaction could be. So some of the trouble. The way target at time equals 0 will describe the reactants. Think again, atom. Okay. We define some coordinates to define well. So we have the possibility which nothing like the atomic we see, doesn't matter. One of the best ways to define this sort of cohesion is we define distance between the two main fragments in the molecule. We will define our states, and then you will define your initial wave packet as a combination of the atom there plus a referential state. Okay, and then okay, if I want to define the other atom coming close to you, I define another distance, and instead of defining like going to one of the other, I define going to the center of mass. That is this way. This definition of this big garden here. And obviously, I need to have the orientation, a diatomic molecule. Okay, I have to define the possibility that they kinds of angles. I define gamma in here. But imagine that they collide and they produce different fragments because the diatomic molecule breaks and then one of the fragments goes with the other atom. And then we have this possibility in which we end up having AB plus C. There is no way that these coordinates can define these product. There is no coordinate that will define these. This is one of the main problems in quantum dynamics. Okay, the transformation of coordinates. Why do we need? Okay, then we go back to the beginning of the course we talk today. You want to collide, and after that, calculate your scattering angle and to see what has happened after the collision. And then using the solid angle, probability, and then blah blah obtain. But if you not define, there is no coordinates that can define whatever happened after collision. You cannot get a proper explanation of what happened afterward. You can get like a total cross-section, like something has happened and something has gone somewhere, but we don't know if it's another type of fragment, same fragment. So you get whatever to a surface. Okay, something has happened. Total cross-section. What is it? You will go individually and see how your wave pattern and where you get the most probability of your wave pattern. This is why we can see how they both where do you get the highest of the probabilities. Okay, so they will be that. But obviously they won't be well defined if you don't have the right coordinate. But this is one of the biggest problems in this. Okay? So if you want to make an analysis of initial state in a final state, if you don't have the right coordinates in here, you cannot get state to whatever. Yeah. Okay. Now, another thing. Just coin. There is no code in the world that can do all of quantum mechanics calculations. No, okay? Because if you have understood a little bit in course, everything is related to the different fragments, how you describe them and how you define the wave function. So then each problem is different. Each problem is different. If you have one molecule, then the definition of your initial wave function would be different. You have atoms and two atoms. You have something that is two. So then there cannot be a general program. This is probably why nobody explains that, because there is no way that they can as you do for the quantum chemistry. You can use this type of basis, you can do a different molecule changing the basis, or a small molecule changing the basis. You can do it here. If you decide, you can this type of calculation, and if you want to do something different, you ask for your code and everything. So what do they do? Everybody that does quantum mechanics, they have their own, they develop. Okay? Some of them, they make it available, and then if you particularly want to study this stuff, use this code. If you want to study this, if you want to study this is why you're never going to find any program that will store your data or not in classical approximation. Classical formula, very complicated. Okay? So most of the groups, as I said, develop their own codes. They are available. There is a code that does very little things, just some sort of elastic collisions in which you start from one particular stage of one of your fragments. Initial fragment can be a diatomic molecule, and then you have another fragment, and then you can collide, and you cannot make a new. It's like elastic. What you can end up with is a different state, internal state of the fragment. So basically, you collide and then you transfer this kinetic energy into gravitational rotational mode. Okay? You go to the molecule. This probably will make your life very complicated. Say that it's not possible that you do it, but you will have to change the code. So that means that the code doesn't do it. Okay? So you have to change the code, obviously the code doesn't do it. So we will use this code because it's kind of easy for pedagogical reasons, because it's easy to see the Hamiltonian. You can define all your input functions, define what kind of function you use, blah blah blah. Okay. So the name of the code is quantics. Is based on the it was the code is based on a very code developed in Harvard University that is called and then my telephone was big in quantum mechanics to work at. So one of the guys who was working there for many years is a guy that I met by his postdoc in the UK, now in the UCL in London. And he's kind of taking the basic MCTDH in quantum classical, classical mechanics, and also dynamics. So there's a lot of other features that nowadays are more common to bigger systems. Fun. So I don't know if you have understood so far. Everything is related to the definition and your wave pattern. Okay, so every particular code will define the in any particular way. Okay, so I don't know how many people. Okay. Not many, so I just think. Okay. So we have this other method, that is the method that we have studied till now, in which we define our wave function depending on your coordinates and the time. Okay, using this variable separation, then we have the function in. Okay, so we have a number of degrees of freedom there, so we have a product of functions of coordinates, Q includes coordinates. Then we have these functions depending on and then we call these function coefficients, and then we have these the basis functions of the degrees. So here that only depends on it. For an efficient and evaluation of this of the action of the Hamiltonian, you have to define functions. So you know that they are functions. This function I get the indicators and everything, but at some point you have to define a performance. Okay? Because it's a function, but you need to define. I want to go from 0 to 9, from 0 to 20 years. So you have to define. So then, the way to describe this is described by the discrete variable representation or finite basis representation. And, they help us actually apply and the evolution. Okay, so you will see here this is the matrix representation. Okay, that was solved by this evolution. Okay, so this is why I said before. So then you have the right side of the equation and you apply the parameter, and you use the evolution operator to actually make it change in time. And usually you have a combination. If you use the evolution operator, they could be changes a little bit. Yeah. So instead of having some functions that are be now in these functions, then what they do is like they define the wave function as a hard report. Think about quantum hard report, exactly the same as in quantum chemistry for these independent products. So then you have a combination of functions that depend only on one of the coordinates. Then you have a degrees of freedom as well. You have the coordinates. What they call MCTD expansion coefficients that are the ones that you find here, and they will evolve as well these. Okay, and then they have the equations of motion. That is, they have to. There's a lot of algebra here because it's a slightly different approximation to the wave function. Okay, because the definition wave function here is a little bit different. If you remember a function, wave function, depending on the coordinates, would be a function of 3 variables. But in here, what they do is a combination of functions that only depend on one. The algebra that they have to apply is completely different. Because if you have a function that is only dependent on one r, you apply some derivative, you have to understand that the derivative in this function is different than in the other one. So there is a lot of algebra just to end up having the equations of motion. It's not what because it's slightly different than you might have with your. So just the final slide, so I made it on time. In MCTH probability, we want at the end, just to obtain a simple indicator section, is obtained out of the flux analysis via a complex observing methodology. That I need to a complex observing potential is basically a function and it makes your wave function disappear. So you have a function in time, blah, changing volume, blah, blah. But at some point, the operation of the computers constantly calculating because it's going fast. And then you have to stop in time, and you have to have a finite grid. Because it's not that I can move the molecule 3 meters away and see for the 3 meters after collision, because actually we are in quantum world. Okay, so we're moving in 10 seconds and we are moving Armstrong and 10 to the minus. Okay, then I need to stop the grid at some point. So then the way in which I know that my function at some point that I will consider that the reaction has actually happened, it will make that my function disappear, so it goes to 0. Because if I don't do something, and my two molecules are colliding and going apart, they will go, and then if they reach your grid, where is this function going? This is the end of the grid. You have a periodic way of defining your coordinate. It goes to the other side of the grid. So you think this. Then you will end up with a function that nothing is ever being. So nothing, okay? So then the potential is something that we put at the end of the grid to avoid no propagation, actually avoid that the function comes back into the game. Okay? So then we make it disappear. Function. You want to know this there is a complex potential that is basically absorbed. There is no perfect complex formula. This is mathematics. And then we play with numerics. Okay? With numerics. We try very hard to get the best as we can a good complex potential. Otherwise, if it is not getting or absorbing or making the wave function is zero, it will go back at some point. So then, converging these type of calculations is hard, very hard, and then look at it. It's super hard. You have a lot of details that you have to see. Okay? But it's something that we need, especially in this program, because the probability this program is connected directly to the company and the flux company. Okay? This is why I haven't introduced it before, because you know the methods they don't use is very particular of this type of so the only thing that we need to know is that it's obtaining complex potential that is defined as this W here. Okay. It can be split in different arrangement terms, different observing potentials in different places of your grid. Okay, end up having different practices. So this way in which we calculate the probability is this equation in which you have this delta E, important thing, I will explain now, and then you do integral using some this expression on your evolved wave pattern multiplied by G. Obviously. Why did I say that this delta is equal? Because at the end, it tells you all these for all the momentum you started with in the beginning. And you want to have a probability that is related to the initial flux, initial number of particles. This is the way you have to do it. You have to divide by the total amount of energy. And this is the parameter that you have parameter, but the information that you give at the beginning, they have somehow related to this probability, which is defined by the global total energy that you started with. Okay? At the end, this is a function that you can make numbers, but they have to mean something. Okay? Everything is related. Everything has to be taken into account. Function, number of everything. Say nothing and when have to compare the frequency. So if you larger basis set, change the if you say, okay, you need to create a wave function that you need to have a set of energies that will give you something, because if you have no energy to actually overpass the barrier, there is no reaction that you have no enough energy to actually move. The wave target will go like that, and you will end that after 3 days with the target not having moved. All these things have to be done. You don't have to do it. These have to. Well, so, just because we will study at the beginning, sorry about that. My problem actually. So extra data. I mean, this is only a few things. For me, the Bible of the quantum mechanics, that is a quantum teaching, from most of you already know. This is the Bible. It's so well written and so easy to follow. There is another very nice book that is even more pedagogical. Parts of David is even everything. So it's a little bit different to the normal quantum dynamics or mechanics. It's a very nice book as well. Some of the articles used in the demonstration this afternoon. All the methods used in these quantics. Okay, this is the second one. Actually, the experiment or the theoretical calculus that we are going to use is in this paper in 2002. And just the reference to the quantics package at the I've been through many, but I just for you to help because I presume that you're going to have the presentation.
Yeah, sure. Yeah.
So then you yeah, you asked me for it. So you can go to all these all details because I didn't give you anything. So well, I hope it's yours. Thank you, Paco and Jess, for inviting me. I see you this afternoon. Please take a lot of coffee because we are going to finish the lake and this is hopefully it will be okay. You can ask. I don't know if it is because you understood nothing, you understood everything, you're shy. I don't know. It's only 2 of you.
So since we got some delay, let's do if you want 10 minutes more for the break. So we are back at 3:20.
Bueno,